Ladies and gentlemen, welcome back to the Simpkins Physics Corner. It's Mr. Simpkins here with some two-dimensional collision breakdowns. So here is the first one. We have a mass of 2 kilograms coming in at 10 meters per second to another mass that is at rest. So this guy's just chilling there. And it's going to be kind of a glancing blow, like they kind of bounce off in their two different directions. So I've provided you with the known information here for the angles. Now, the big idea behind all of these problems is that the total momentum before a collision has to be equal to the total momentum after a collision. Now, the added layer, if you will, is that that statement is true for the total momentum in the x direction and the total momentum in the y direction, right? So we have to look at our x-axis momentum and our y-axis momentum. Now, this problem actually is pretty short if you do it correctly, and here's why. At the beginning, our initial y momentum is 0, because the ball is only moving horizontally. So could you do this problem with horizontal momentum? You could. We're going to do the next one with it. But look at how we can shrewdly approach this. If we know that the total momentum in the y direction before the collision is 0, that means that the total momentum in the y direction after the collision is 0, which means that the momentum in the y direction for object 1 has to be equal to the momentum in the y direction for object 2. Okay, so we'll call that one object 1 and the bottom one object 2. Let's go ahead and fill this in. So we got mv1, I should say m1v1 equals m2v2. All right, sweet, and we plug this in. So we have 2 times, now here's where it gets tricky, okay? We are looking at the y direction. So I should actually have written v1y and v2y like this. And so there it is. So we have 2 is our mass times v1y. Okay, so let's talk about v1y. If we know the direction and the magnitude of this vector, the magnitude is 6 meters per second and its direction is 50, then based off of the horizontal, if that's our relative angle there, this would be your y component. And if you look at the trig behind that, if the resultant is the hypotenuse, the y component is the opposite side. And so we use the y component, or we do v sine of theta. All right, so we're looking at the y component, and we have to set those two equal to each other. Now, over here, we're going to do the same thing. We're going to say this guy has a mass of 1 kilogram, and the v here, remember, we're looking for the y component. So how would we find that? Well, it would be this guy, right, which again is opposite, so we're using sine. But the velocity itself is unknown, so it would be v sine of 45. So sorry about my bad whiteboard etiquette. I kind of wrote off to the side here, but let's clean this up a little bit. All right, do I have my calculator? I do. So 2 times 6 times, make sure in degree mode, sine of 50. That means that 9.19 over here is going to be equal to 1 times sine of 45 times v. So we got v and then times this, which is represented by 1 times sine of 45, which is 0.707 if I round it off there. So now you just divide both sides by that, 0.707. And that gets you your velocity. It gets you your final velocity there. So 9.19 divided by 0.707 gets you pretty much 13. So in this first problem, we noticed that we had no initial y momentum in the system. And that means that the total y momentum in the system after has to be 0, which means the upward y momentum of the mass 1 has to equal the downward y momentum of mass 2. So that's why I set them equal to each other. Now, technically, are they equal and opposite? Should I have a negative in there? Yes, but based on the decisions that I made, I just said, hey, their magnitudes are equal, so we can use this idea that the up momentum is equal to the down momentum, and we went from there. So that's how you solve that first one. Let's look at our second one here. Let me pick a different color so I can write this out here for you. Okay, here we go. Using the conservation of momentum, solve for the final velocity. Okay, so oh no, sorry, that's the first one. This one says solve for the initial velocity of the purple puck. So now this is unknown. All right, so let's go ahead and see what we have here. Well, at the beginning in our system, we only have delta p x initial, all right? And that's going to be mv, which is very easy to calculate, except we don't have the mass. So I'm going to leave it like this. That's the initial momentum in the x direction for the system. Now, they will collide. Will the mass 1 and mass 2 get some kind of vertical momentum? Mass 1's positive, mass 2's negative. Sure, it will, okay? But we are interested in the horizontal initial velocity, so let's go ahead and take a look at the horizontal momentum in this problem. and see if that will inform us about this. What we can say here is that the total momentum in the x direction after the collision is going to be made up of those two momenta added together. But again, we are only considering the x component of momentum, which is this one, and based on the angles we're given, that would be your adjacent side, which would cue us to use cosine because of adjacent to hypotenuse. And so we would have, let's see, so px1 and px2, we're just going to add those two together. So px1 is going to be 3 kilograms times 2 meters per second, but we're looking at the x component, and we use cosine of 20. So we got to take that guy, and then we got to figure out the x component of momentum for the second mass, which is 2 kilograms times 6 meters per second times cosine of 40. Okay, sweet. Now again, both of those things are bringing horizontal momentum to the table. So if we want to find the total momentum, we got to add them together, and that'll get us our final answer. So 3 times 2 times cosine of 20 plus 2 times 6 times cosine of 40. That's going to get us 14.83. Sorry about the slash there. My whiteboard messes with me sometimes. All right, there it is. Now, that would be kilogram meters per second of momentum. Let's make sure we know what we're actually solving for here. So, where do we go from here? Well, final step. All right, over here, you can think of it as doing a PMV stack even if you want. We know that the mass is 3 kilograms, and since the purple object is the only one with any horizontal momentum before the collision, it gets all of the horizontal momentum that is equal to the momentum after the collision. Saying momentum a lot is really fun. And then if you use P equals mv, or you rearrange it here, you have P divided by m. That'll get you your final velocity, or should I say your initial velocity for that first guy coming in there. So our velocity here would be 4.94 meters per second. Okay? So that is how you solve those first two. Check out the third video. I linked a video from another channel. You can check that one out if you're getting stuck here for this example. It does get a little crazy with the algebra because we have two unknown velocities, but with a system of equations, it's definitely manageable. So until next time, I'm Mr. Simpkins in the Simpkins Physics Corner.